Hey class, Absolute 5 here, and today we're going to talk about sets. What are sets? You might be wondering, what are sets? So the thing is, the definition of a set is this. A set is a collection of objects, each called a member or element of the set. So now what are you trying to explain is what you're trying to think. So let's just take this example. Let's take the natural numbers. What are the natural numbers? Well, they're 1, 2, 3, 4, 5, dot, 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 and so on. All the numbers in all existence, they are in this set. That's what they're called, the natural set. Now, what are the whole numbers? Well, they are almost the same set, but what's the difference if you can spot it? Obviously, it's the zero. What makes them different is the fact that this set has one more element in this set than the other set. So for example, think of the first set as a collection of all the numbers in the whole universe. So it's, in a sense, you're talking about a set of infinity. And that this is the infamous thing where you have an infinity in the other example, but plus 1. So ideally, this set has more elements. The whole numbers have more elements than the natural numbers. Now, why are we talking about sets? Is because we need to determine whether or not something is either equivalent, greater than, or less than, or equal than, which I'm pretty sure you are familiar with the inequalities symbols. So we all know equality would be A equals B, and A and B are whatever elements are there. Obviously, inequalities, I'm pretty sure you know what each one is. Inequality is greater than or equal to, less than or equal to, so strictly greater than or strictly less than a certain object. And also there's another sign that's true, and that's true for not equality, is that. Just for the record, I'm just going to write it here. Greater than or equal to, less than or equal to. This is strictly greater than. And this is strictly less than, and this is not equal. Not equal at all. Okay, so for example, if I want to determine that, if I want to make this statement true, what would I have to put here? 2 is technically less than 3, so you'd put the strictly less than symbol. If I put 72 is less than 27, is that true? No, that's false, because 72 is not then less than 27, it's greater than. What about 8? My question now is 8 greater than or equal to 8? Yes, that's a true statement. Why is it true? Because it's equal to. It may not be greater than itself, but it is equal to it. We'll do one more. 23, is that less than or equal to 0? No, it's false. So ideally what you want to, in essence, what you can actually think about is this. If I took the natural numbers, right? If I took the natural numbers and I compared it to whole numbers, which one is bigger? Obviously the whole numbers, so natural numbers are always less than whole numbers. But ironically, there's a set bigger than both of them, and that's integers. What makes integers different than whole numbers? Well, basically they include negative numbers and 0 and every other positive number. So ideally, integers is greater than whole numbers. But there's a set even bigger than that, which is rational numbers. Rational numbers are numbers that end, like their decimals will end, but they also include fractions, which integers do not include. They just include regular numbers, whole numbers, I should say, and so forth and so on. Obviously, dot, 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 and this is also a dot, dot, dot there. So you know what I mean. All the numbers are there. Now, what's the difference between a rational and irrational number? The reason why I said rational numbers, their decimal places, it eventually ends. Or you could, if it repeats, you know to abbreviate it as, bar at this point. But the decimal point, it eventually ends. The thing is with the irrationals, they never end. They just keep going on and 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 on. But the decimals does not stay the same. It'll always change. So for example, you've seen this symbol, obviously, which is pi, which is 3.141592. That's as far as I can remember off the top of my head. So ideally, this number is going to go on forever, and scientists themselves have tried to calculate this number to like the billionth place with computers, and it's ridiculous how far this number goes. It goes on forever. Or square root 2. It goes, I think, 1.71 something. That number also goes on forever as well. So you see how the numbers, they don't tend to, they always never repeat, but they keep going on. That's irrational. Compared to, let's say, if you look at a half, it's just 0.5 and it just stops. You see how rationals, they just stop, and irrationals, they just go on forever. So, it's a nice example to think. So here's the thing. Rationals and irrationals, they're greater than integers. They're both greater than integers. If anything, they're both kind of like tied in their own class. Like rationals aren't bigger than irrationals, and irrationals are not bigger than rationals. But what is bigger than both of them are real numbers. So basically, all numbers that corresponds to points on a number line. So in the end, in summary, if you look at this, real numbers are for now, they're the king of all the sets. Then you have irrational, and you have rational numbers. I'm just trying to write this here. From the rationals, you have integers. Then you have whole numbers. And finally, you have the little natural numbers. So it's kind of cool to think of infinity in these types of ways. So that's the lesson for you guys. I hope you enjoyed the video. This is, be sure to like, share, subscribe to my channel, mash the bell button, and I'll see you guys next time with another video. This has been Absolute 5. I'm Roger Palomino. Math is infinite because there are infinitely many possibilities. And don't forget, don't hate, calculate.